Welcome to the last lecture of module 5, which is design of general purpose industrial helical gear reduction unit part 3, and this is lecture number 26, where I will show how the input shaft design verification is done. It is also included in this lecture the bearing life estimation. This means that what we did for output shaft in last two lecture, that will be for the input shaft in a single lecture, because procedure is more or less same, only we have to be careful about the loads, moments, etc., etc. Now, in this lecture, therefore, first of all we will look into equivalent loads, equilibrium, input shaft sub assembly, and then input shaft force equilibrium we will consider, and from there we will find the reaction force and then bearing life estimation, loads on left end bearing and bearing selections, design verification by calculating factor of safety. Also we will consider the right bearing, which is not written here. That means, we will calculate the load in the right end bearing also. Now, finally, I shall make a comment on this shaft assembly and maybe overall comment on this week 5 lecture. And this is already explained that we have considered modified the design a little bit to have the parity with the week 4 lectures and for easy understanding. So, we are considering this figure only, and the same thing it is written here, already it is repeated in earlier lecture. Now, directly we are coming into the input shaft. On the input shaft, as we find, input is from the left hand side, direction of rotation is given, torque is given, and then the loads on that shafts what are coming over there, that are also shown here. So, at this stage what we have shown that this is the I think the all total loads are shown here. So, better it is we should go for this. Okay. So, we have considered the all loads on the shaft, right. The pinion, it is rotating in the clockwise directions. If we consider this is the plan view, okay. No, this is we are considering the elevation, and that is in the plane of slide, x y is that plane. Now, here if we consider this contact point, if we consider the tooth mesh, that is in the back side of this slide, that means, this is below the slides, you can say, because the contact was there and it was rotating like this. Okay. So, due to that, you can say that when this teeth is coming like this, it was pushing the gear in the upward directions, pushing the gear of the intermediate shaft in the upward directions, and that is why due to this helix angle, axial force has to become in this direction. This is the axial force. Okay. Now, as this load on the right hand side, right hand support bearing, due to the tangential load and the radial load will be more than the left hand side. So, we have locked this left hand bearing. If you remember the drawing when developed, we locked the left hand bearing, it was fully constant. That means, fully means it was able to rotate, but it cannot move in x y directions. Okay. It is locked to the shaft as well as to the housing. So, this means that this, if we consider the bearing reaction, it is here, it is acting in these directions. Now, the question is that it is sometimes it is a little confusing. Actually, if we consider that bearing at this end, it is fixed, okay, and the applied load is pulling. So, bearing what the load offering to the shaft, this is in the opposite directions. That means, bearing is pulling the shaft in the left directions. That is why the sign has become like this. Students used to ask, sir, why it is on the bearing it is like this. You have to visualize at this point. Now, suppose if we change the direction of rotation, in that case if we change the direction of rotation, this axial load direction will change. Here at this point it will be in this directions, and here it will be in the opposite direction, or else if we change the direction of helix angle also, then for the clockwise directions the load will be like this. So, that I think this is not very difficult to understand. One can put some time to understand this, and then he can go for the right diagram. Now, also in this section what we have shown all reactions that moment due to the axial force, everything are shown here except the bending moment. Bending moment it will not come in this picture. So, we have not shown, right. So, while you are reading this, you can spend more time on these slides to understand how it is acting. Now, we have considered the right bearing, right hand bearing. Now, in this right bearing, as you know that no axial force is acting, as there is a radial loads are more. So, in the same way what we calculated in case of output shaft, we have calculated the load here, and bearing loads we have designated as by B. B means load acting on bearing. Then next comes Y or Z, that means that is the directions, and then comes R as a subscript, which means it is right bearing. Now, if we observe this bearing very carefully, what we have shown here, it is fixed. This actually means it is with the housing, this outer race is held, it cannot rotate. But if the question comes whether it can move x directions or y direction, the answer is that this cannot move also in the x y direction, this can move in the x y directions, as this bearing is not locked with the shaft. Okay. And what are the load coming over there? That is why we find that there is the component of tangential load, component of radial load, and they are acting in y and z directions. The magnitude etcetera are given there itself, and then we shall go for bearing life calculations. This is the direction of rotation is shown also here. Now, this is locking arrangement we have shown. Now, we are calculating the equivalent load acting on the bearing. Now, clearly in the equation of equivalent load, P is equal to C1 x V F r plus Y F A, that 1.5 the factor we have taken for it is a medium shock load, but x factor is for that series of bearing it is 1, and the race rotation factor is also 1, because the outer race is fixed, which is shown here, and there is no axial load. So, the Y F A component vanishes, and ultimately from the load shown here we calculate that equivalent load is 1307.36 Newton. Then life of the right bearing in revolution is ln is equal to that is 21,400, which is the dynamic load capacity of the bearing. This is bearing, I think I have shown at the last pages. This is in pound, it is given as 4800, which becomes 2100 Newton. Okay, 2100 Newton. So, life in number of revolution is nothing but that C by P to the power a factor epsilon. In this case it is 3 as it is a ball bearing multiplied by million of revolutions. So, that becomes for this case 4386 into 10 to the power 6 revolutions, and if we calculate the life in hours, this input shaft is rotating at 1500 rpm. So, in hour it is 1500 into 60 rpm, and that we divide the number of life in number of revolution by that amount, which is very large. The value is coming 48,732 hours, whereas we are expecting only the life of minimum life of 10,000 hours. Now, here we shall check the other bearing and then we will make some comment on this issue. Oh, here itself this is much more than specified minimum life of 10,000 hours, and it indicates that lower series bearing and with one size less may be well satisfactory. We have chosen 6306, probably 6205 also satisfy the life. Now, if we look into the shaft, then what we have done, we have reduced the shaft size up to 30 millimeter to have the output input end of 25 millimeter. But if we go for 25 millimeter bearing, then probably that shaft input size will be reduced to 22 and 23 millimeter, but that is possible because after in between that there will be one seal. That seal is available almost every 2 millimeter. So, that means, if we take a bearing of 25 millimeter inside the, probably we can make the shaft diameter at for the oil seal 24 millimeter and shaft diameter probably 22 millimeter or even 22 and half millimeter. So, that is acceptable, and there are also different type of locking arrangement is possible. In fact, after the bearing we can put a bush there, and after that we can a sleeve there, and then we can put a coupling. Okay. So, that we will, when we will make the detailed drawing or plan view of the housing, we shall discuss again about this matter. But next that if we consider the left hand bearing, the same way we have calculated, but in this case we have the axial load. So, for that axial load what we find, here we have written this is fully locked with housing, also inner race is locked to the shaft, axial movement is fully constrained. So, in that case again what we find, the load still including the effect of here, if you look into this factor 1.6 into this axial load, that we have considered because y is 1.6, but still including that it is less than the other bearing. However, the life becomes 81,320 hours. So, it is 8 times than what we are expecting, and the comment is same, probably we can compromise with 6005. Okay. We will look into this matter after this. Okay. Now, we shall go for calculating the bending moment in the vertical plane. The same way what we did for output shaft, we shall also analyze the input shaft. I would like to mention here, if we look into the direction for two stage gearbox, direction of rotation of the both shaft, okay, in the same directions, and direction of helix is also same. Okay. So, you will find mostly the loads are in the same directions they are acting, and there will be not much difference in the technique of calculating the load, bending moment, etc. However, in case of output shaft, the gear is in towards the left side and here it is in the right side, only that difference is there. The pinion is close to the right bearing. In case of gear, output gear, it is close to the left bearing. However, this is the bending moment, torque diagram, shear force diagram and bending moment diagram we have developed, and then we consider the horizontal plane. In the horizontal plane, as we find that the direction of moment here in such a way that it has the load due to that has been the coupling, this couple force has been added to the right hand bearing and it is subtracted from the left hand component which came from the radial load. Okay. So, ultimately if I say, this means that this was reduced by the couple force and this is increased by the couple force, but here at least directions are not confusing like the output shaft. Okay. And on the basis we have drawn the shear force diagram and then bending moment diagram. We have to be careful if we remember, we have to be careful that here when this moment we are taking from the left hand side, then we should remember as there this moment due to axial force is acting by the left hand side of the shaft and the right hand side of the shaft, the moment will be different, but maximum moment always we should take the what the maximum magnitude considering plus minus side of the bending moment is there, that we need to consider. Now, looking into the feature of the shaft, the critical moments, the critical most section will be the section 1, as the resultant bending moment is maximum there with some stress concentration due to the integral pinion. Now, this means that if we consider this section, probably this will be the critical section. Say as we go towards the right hand side or towards the left hand side, the moment decreases from that value. However, this torque is somewhat like this, torque is say it is starting from here to here and this will going like this. So, torque will be there from this point to this point. Here torque will be somewhat less if we want to the average load, but in that way probably the next critical section would be like this, but here the diameter is more or less same, whereas stress concentration will be more in the mid section. So, probably verifying the factor of safety for that section 1 will be good enough to verify the design of the shaft. Now, another thing is there, the material of this shaft contrary to the output shaft is EN 19, for which the strength allowable strength are much more. Okay. And if we consider the bending moment and other, if you remember, if you look into the 2 slides before that, we will find that amount of bending moment is not much there. So, therefore, without calculating we can say that this shaft design is highly satisfactory, and as already discussed, keeping the dimensions up to the step of bearing same for the shaft, keeping the span length also same as in the shaft, we can simply reduce the 2 diameters of the bearing seat. Remember that if we change the direction of rotation or helix angle, then load distribution over this bearing will be different, and due to that we do not want to use other size bearing. Of course, it can be used also, but from the inventory point of view it is better to have two same bearing in a shaft, and instead of 6306 even we can go for 6205, that means 25 millimeter diameter, and as already discussed we can make this shaft input end instead of 25 millimeter we can make it 22 millimeter. However, in between if we can check these calculations, this will not be shown, that calculation will not be shown, maybe can be you can verify with through the assignments, when the assignments will be there. And next stage when we will develop the full drawing, that means plan view, complete the plan view, we can change the shaft diameter and we can put those bearing there. Okay. And in practical cases, if it is in the industry, probably here that decision will be taken to change the shaft diameter, and a design calculation will be repeated to verify, and that design calculation should not take much time, because of the reason procedure will be same, only one has to calculate that what is the maybe week, 1 week, not more than that, and we can again arrive into the new design. And I would say this is the end of week 5 lectures, where we have gradually shown the gradual development of the different shaft, sub assembly, their locking arrangement, bearing selection, shaft design verification, it has been done. Now, straightway we can go for the plan, completing the plan view, that means with housing, cover, seal, etc. But there is still one point is left, that is we have not yet verified the design of the key. So, we need to design, we need to verify the strength of the key from their failure point of view. In that case, if necessary, we have to increase the width of the gear, if necessary we have to increase the hub for the gear hub portion. So, that verification we need to do next, and then we can finalize. But from the experience I can say that while we go for the design, I mean detailed drawings of the plan view, we have two options. One, that we can straightway reduce the bearing size and we can develop, or we can keep this gearbox as it is. That will because intentionally in the intermediate shaft, as I told, life is around 22,000 or more, still we accepted that one, because this gearbox, although it is being over designed, but that can be used for the specific problem what we have completed through this lecture, or else it can be, along with that it can also be used for higher load. Say instead of the say starting torque is 200%, but the shock is very high shock load, or this gearbox everywhere we have taken the factor in such a way, probably it can be used for some other I mean higher value of input torque with the similar cases. This means that probably instead of 30 Newton meter with 1500 RPM, probably we will be able to go 45 Newton meter with 1500 RPM, and same gearbox can be used. So, at this moment I would like to make a comment for that. Just in the process of learning, what we have taken, it is slightly over designed. This gearbox need not be mixed such a everywhere, the dimensions is more, even in module we have taken a little more, that need not be. But anyway, in the next week we shall complete the drawing, and then I shall make the end lecture that what really in practical cases what really we need to do. So, thank you once again.